I'm going to talk about finding the tree height and tree traversal. Height in a tree represents the distance from the root node to any given leaf node. So if you look at this example over here, the root node is 9, that's height 0. But if you see 4 and 17 here, that's height 1. 3, 6, and 22, height 2. 5, 7, and 20 are height 3. So it's the distance from the root node to the leaf nodes. They're kind of like layers of a cake, and that's how you're going to count them. Different paths in a highly branched tree structure may have different heights. But for a given tree, there will be a minimum height and a maximum height. And if the tree is balanced, these values will differ at most by 1. So before I show you the code to implement those things, I'm going to show you the use of the code. We're going to go all the way down to the bottom where we create a new binary search tree, and then we add all these values, which those values there are the same values as in the picture over here. We're going to find the min height, we're going to find the max height, and we're going to check if it's balanced. Let's just comment out these now. So it's showing the min height is 1 in the console, the max height is 3, and it's not balanced. The min height is the distance from the root node to the first leaf node without 2 children. So if you look on here, 17 is a root node without 2 children. It has a right child, but it doesn't have a left child. So the minimum height, you start at the root node, which is 0, and then you count to the next level, which is 1. So the min height is 1. Now the max height is just the distance from the root node to whatever the most bottom node is. So 5, 7, and 20 are all at the max height. So 0, 1, 2, 3. So the max height is 3. Now this tree is not balanced, because remember, if a tree is balanced, the values between the min height and the max height will differ at most by 1. You can see that there's a missing number here. The reason why this tree is not balanced is because there's no number here to the left of 17. But if I uncomment out this code here, we're going to add 10. Now 10, if you see, when it's being added, it's going to add to the left of 17 because it's more than 9, but it's less than 17, so the 10 will fill this spot right here. And then we're going to find the min height, the max height, and then check if it's balanced again. Okay, so now the min height is 2 and the max height is 3. The min height is going to be either this 3 or the 10 that we just added. It's not showing up in the picture, but just imagine there's a 10 right here. So we have 0, 1, and then the min height is this level right here, because this is the first level that there are nodes without 2 children. If you imagine there's a 10 right here, so that's 2, and then 3 is down here. Right now, is balanced is true. The difference between the min height and max height is at most 1. So it's going to have to be either 0 or 1 to be balanced. When a tree is balanced, then searching through it is much more efficient. We're not going to cover this in this video, but there are ways that you can make a tree automatically balance itself when you add new items and when you delete items. This creates greater efficiency when searching the tree. Okay, now we're going to look at these last lines I have commented out here. These are ways to traverse the tree. Tree traversal methods can be used to explore tree data structures and basically find all the values in the tree. In depth first search, a given subtree is explored as deeply as possible before the search continues on another subtree. When I show you an example, that will make more sense. But there's basically three ways that this can be done. There's in-order traversal, pre-order traversal, post-order traversal, and this last one I'm going to talk about later, this level order traversal. So let me run this and then I'm going to explain it. So here you look at the bottom of the console and you can see what we've logged here. For in-order traversal, you're going to begin the search at the leftmost node and end at the rightmost node. So you can see this just has all the numbers in order. 3, 4, 5, 6, 7, 9, 10, 17, 20, 22. Those are just all these numbers in order. You're going to begin at the leftmost node and you're going to add all the numbers in order. Now, pre-order traversal, you're going to explore the root nodes before the leaves. So let's look at this. I'm going to read off these numbers down here and I'm going to show up on the picture where they are in the picture. So we're looking at the root nodes first. In the list, 9 is first, that's a root node, then 4, that's a root node, then 3, and the next root is going to be 6, and then 5, and then 7, then 17, and then 10, which we don't have on this picture, then 22, then 20. So the pre-order focuses on the root nodes first and then adds the nodes below that. The post-order explores the leaf nodes before the roots. So look at this one. The first node on the list is 3 because it's a leaf all the way down. And then we have 5 because that's a leaf node. And then we have 7. And then we're going to go to 6. We're not going to hop over to 20 over here because that's on a completely different branch of the tree. You have to finish all the leaf nodes on one branch before you go to the next branch. So after 6 is 4. Now is where we jump over the leaf nodes on the next branch and we use 10, which again is not on the picture, then 20, then 22, then 17, then 9. This level order is called a breadth first search. This explores all the nodes in a given level within a tree before continuing on to the next level. First it's going to do level 0, which is 9, if you see these numbers on here. And the next is going to show 4 and 17, then 3, 6, 22, then 5, 7, 20. So let's go over the code. So first we're going to go over the code for the min height and the find max height, and the is balanced. So the is balanced is pretty simple because you just call these functions that I haven't talked about yet, but you're going to call find min height and see if that's less than or equal to find max height minus 1. So this is going, since this is a conditional statement, it's going to return true or false. So as an example, if you remember before we added the 10, we had the min height of 1 and the max height of 3. If this dot max height is 3, 3 minus 1 is 2, so is 1 less than or equal to 2? No, false. So we know that the tree is not balanced. We have false right here. But then we run it again down here, and the max height is 3 and the min height is 2. If we do 3 minus 1, that's going to be 2. So now we have, is 2 less than or equal to 2? Yes. So we're going to return true. So that's how we're going to find out if it's balanced. Now let's look at find min height. This is going to be a recursive function. You can pass in a node, but if you don't pass in a node, it's going to set the node to the root node here. And then it's going to check if the node is null and return -1. If you haven't added anything to the binary search tree, it's going to return -1 for the height. We're going to set the left and right to calling the find min height on node.left and find min height node.right. So this is where the function becomes recursive. Eventually one of these two is going to be -1, because the left or right node is going to be null. So here we are going to add 1 to the left if left is less than right, and we're going to add 1 to the right else. So if right is less than left. And for find max height, it's the opposite. So instead of having the less than here, we have the more than here. So here we're going to return left plus 1 if left is more than right, else return right plus 1. Feel free to check the code in the description to play around with this yourself. The in order, pre-order, and post-order, there's a lot of similarities to the code. So let's look at the in order traversal first. The only thing that's going to be different in each of these in order, pre-order, and post-order are these 3 lines. And the only thing that's going to be different in those 3 lines is the order of the lines. So for all of them, we're going to check if the root is null and return null. That's just to check if there's even a binary search tree that exists or if there's any values in it. So if we find out that there is a binary search tree, we're going to do these things. We're going to create a new array of the result, and we're going to add each value in the tree onto the result. So we're going to create this function, traverse in order function, and you can see down here we're going to call that function and pass in the root node, and then after the function has been run, you're going to return the result. So inside this function, it's going to be recursive. And remember, these 3 lines are the only thing different between in order, pre-order, and post-order. It's going to change the order that we check things. So in order, we are going to first do this line. So this right here is short circuit evaluation. Whenever JavaScript evaluates the AND operator like this, if the first thing is true, it will also run the second command. If the first thing is not true, it will not run the second command. Check my video on short circuit evaluation to find out more about that. So if no.left is true, that means if no.left exists, then we are going to run the traverse in order function on no.left. And that just calls the same function again and passes in no.left. Then we're going to push node.data. So we're going to push the value in that node onto the result array. And then we are going to check if node.write exists. If it does, we are going to call the traverse in order function on node.write. And if we look down here, like remember I said that just these 3 lines are different. So in pre-order, it's going to push first, and then it's going to call the function on node.left, and then it's going to call the function on node.write. In post-order, it's going to call the function on node.left, then call the function on node.write, and then push the data. So just the order that we call these commands is going to change the order of how we get the result when traversing the tree. Again, you can check that code and play around with it until you can figure out exactly how it works. I'm going to go down to the level order function. In this method, we start by adding the root node to a queue. Then we begin a loop where we dequeue the first item in the queue, add it to a new array, and then inspect both its child subtrees. If its children are not null, they are each enqueued. This process continues until the queue is empty. We are creating a result array that we are eventually going to return. Now here's just the queue array. This is just a temporary array that we're using that we're eventually going to put things off that array onto our result. If this.root is not null, if there actually is a binary search tree, we're going to push the root node onto Q. This is a while loop, so it's going to continue going through this until we've actually added all the elements from the tree. So while q.length is more than 0, we're going to keep doing these things. So first we're going to let node equals q.shift. Now shift just takes off the first element in the array and returns that element. So we're going to put the root node into node because it started out as the root node, and now Q is not going to have that root node on it anymore. And we're going to push node.data onto that result. So we just pushed 9 onto the result. And if you remember, 9 is the first thing in the level order result. Now, if node.left does not equal null, we are going to push node.left onto the queue. And if node.right does not equal null, we're going to push node.right onto the queue. And then we're going to go back through the while loop. We're going to take off the first node and put it into node, which remember is going to be node.left that we push on here. And we are going to push that value to the result. So we're going to push 4 to the result. And now we're going to push node.left and we're going to push node.right. So in the queue, we're now going to have 3 and 6. But when we go back through the while loop and we shift off an element, even though we added 3 and 6 in the last iteration of the loop, the node that we're shifting off is going to be 17, because shift is going to take the first item of the array off, and 3 and 6 are at the end of the array. So then it's going to get that value, and so on. It's going to keep going through this until it's gotten every value